I feel like you should start with a disclaimer, if not a word of apology, because after all these fancy talks on machine learning and generative AI, here we'll go back to first principle physics and good old engineering. So my name is Étienne Lac. I'm a research engineer for Safran. Safran is a French company in aerospace and defense. And today we're going to talk about CoSApp, which is a Python library that allows you to model, simulate, and design systems, modeling industrial products. It's distributed on PyPI and ConforgeForge, and we have an online documentation on Read the Docs. CoSApp is essentially, so it stands for Collaborative System Approach, and it's essentially a simulation design toolbox to help you design multidisciplinary systems. So with this toolbox, you can do things like single and multi-point design, mono-objective optimization. We can also simulate dynamic systems, and in particular, multi-mode systems. So these are three major features that we'll cover today. And you can also do meta-modeling and a lot more, but I won't have time to cover all the features. The main target is the agile exploration of new ideas, new concepts that engineers may have, and you don't start right off the bat by doing super duper fancy finite element simulations or CFD, and you start from smaller size models. So we target low to middle fidelity models, but with a high emphasis on strong coupling, okay, multidisciplinary systems. So the main concepts are fairly simple. The most elemental unit, the most fundamental brick we call systems, and they're essentially simulation units with a predefined input-output interface. So in this case, you have X, Y, that spits out Z. Once you have that, you can assemble those into a broader system in a larger context. So assemble system into higher level assemblies by connections. And typically when you get strongly connected systems, you'll end up eventually with loops, as you see, between B, C, and D. So that requires an iterative process to equilibrate those loops, and CoSApp will detect and solve them for you. The third notion that we'll cover today is the notion of what we call drivers. And drivers are essentially algorithms that are separated from your model, that you attach to your model to solve it in a way that suits your needs. And I'll give an example of that. The base API is the following. So users can define their own ports. Ports are essentially passive objects that transport data from one system to the next, and they only contain variables. So you see that, for example, if I have my ABC ports, you use the base class ports from the base API of CoSApp, and you add the variables that you deem should belong to are physically consistent to appear in a single port. You can give default values. You can assign units. And CoSApp will convert automatically units. If you connect systems with the different unit systems and units are compatible, you'll have on-the-fly conversion, which can be handy. You can also restrict the kind of data types you want to store behind a variable. And also you see that for variable C, for example, you can store non-numerical value. It can be, so here it's a dictionary, but it can be a mesh. It can be a CAD, it can be anything. Okay. Systems on the right-hand side are the units that I said that transform data. And so if you write your own system, your own model, what you have to do is to specify three separate methods. The first one is the setup method. So that one is mandatory. That's where you specify the structure of your system. So that's where you're going to say, here's my inputs and outputs. You may have subsystems, and you may have to define what data goes from what system to the next. That's also the place where you'll enter intrinsic constraints, like you have physical equations that you want to be solved within that system. And the last thing is events, which pertains to multi-mode systems, which we'll cover in the end. So very specific to CoSApp. The second method is compute. So compute is the number crunching part of your system. That's where you specify how your inputs are calculated from the inputs. Okay, easy enough. And the transition is where you specify how the system reacts to the triggering of an event. And again, we'll cover that through examples. So simple example of systems. So on the left-hand side, you have a standalone model. That's a very simple linear model. So you have three input variables, A, B, X, A being the slope, and Y being your output. And in the compute, you simply say Y equal AX to B. Okay, easy enough. So you then expose to the word a box that says A, B, X come in and Y goes out. Okay. Now, if you go to a higher level assembly on the right-hand side, you see that we have here we reuse two instances of a linear model. That's a bit of a stupid assembly, but just for the sake of example. And here you can connect instance M1 and M2 with a mapping, with a variable name mapping Y to A. So this is this connector here in the end. So it's a typical chaining where one model computes something and conveys it to the next system. Okay, but you can also interact with your parent system by what we refer to as pooling. So you see that M1, for example, pulls variable B. B is an entry, an input of M1. And what happens is that CoSApp will extend this branch here and consider that B is an input of the parent system that's transferred down to its direct child. Okay. Here you notice that the two systems pool X, the same variable name. So what happens in this situation is that X will be exposed at the parent API and will cascade down to the two subsystem in a synchronized way. So that way you can synchronize subsystem inputs. And when you pull an output, so in the case of M2Y here, it's this arrow here. That will appear as a connection from the child. So the output is primarily computed by the child and it's pulled up to the parent. And so the box you've just created here will be visible from the outer world as X and B come in and Y comes out. So drivers. Drivers are modular simulation units, and they're in fact objects that you attach to your system, and their responsibility is to change the state of your system to achieve a certain goal. Okay, so it's a long sentence to say that essentially it's a solver. So, but the originality is that we want to separate the model from the simulation use case. So the model really reflects what the physics of your object does. But with this object, you may want to perform some design. Okay, so you may want to say compute X such that Y equals 0, or you may want to perform optimization, and that's what comes in the little example on the bottom left corner. You see that you instantiate your model here, and you add a driver to your model and of kind optimizer. Then you set your optimization problem, minimize Y with respect to XB and M1.A, for example, set up your constraints, and then you execute this run drivers command, and it will solve your problem. Drivers are very flexible objects. You can first thing you notice that you can write them in sequence. So if you have driver 1 and driver 2 attached to the head system A, what will happen is that they will be executed in sequence, and each one will retrieve the object in the state that the previous driver will have left it. Okay. You can also nest drivers. Okay, so it's this weird assembly that you see here on the right-hand side, and I'll explain that in a minute because that can be interesting. And you can also attach driver to any level of the subsystem tree, and that gives you more control on how your system is exactly solved. So for example, if you have this lower left branch of your tree here, A1 and systems below, any system attached to the top will understand that this subtree is computed on itself, and it doesn't need to solve for any constraints bearing that the system bears. In particular, this loop here will not be solved if you attach the solver here. Okay, so but that's a bit of a more exotic situations. Usually drivers are added onto the top head systems. So example of nested drivers, you may think, why on earth would I want to nest solvers? So it's the fundamental mechanism by which we do multi-point design, by essentially nesting two drivers that we call run single case that represent operating points. And by doing that, you can impose constraint at multiple operating points while solving global constraint on your system. Again, I'll show you an example in the next slide. If you, for example, choose to put a time integrator inside an optimizer, what will happen is that at every iteration of the optimizer, the time integrator will be invoked, and so the trajectory of your system will be computed, and the optimizer will retrieve the state of the system at the end of the time trajectory. So typically, you use this assembly to optimize the initial condition of a system in order to minimize or maximize the output of a time trajectory. Okay, and in this case, we have a simple ballistic model with a freeform model, and we compute the velocity here that maximizes the distance of the throw, okay, just by nesting two solvers. If you decide to flip the logic of this assembly and to put an optimizer inside the time integrator, that what you'll end up doing is solving an optimization problem at every time step. So very different simulation scenario, but using the same model and the same basic objects. Here's an example, an interesting example on multi-point design that we published in an article on the Journal of Open Source Software on CoSApp last year. That's the multi-point design of a rocket nozzle. So typically what happens in the rocket nozzle is that you have pressure and temperature conditions that come out of the combustion chamber. And as the flow goes through a throat, you usually achieve sonic conditions, and you want to become supersonic in the diverging part and create to maximize the thrust of your engine, okay, of your nozzle. Ideally, so in space, what happens is that you have an isentropic expansion all the way through, and your thrust is maximized. But in between, you may have shocks inside your nozzle, which will reduce your thrust, and you want to minimize that. And that depends typically on the ambient pressure that the nozzle experiences. Okay, so essentially the altitude. And there are two important parameters here, geometrical parameter, that's the area of the throat, and the area of the exhaust section. Okay, so here you see on the right-hand side the CoSApp code that you'll have to do to design this system. Nozzle area is the code, the model that computes, that predicts this possible flow regimes given all the rest. Here you have an input flow port that bears the pressure and temperature that we initialize to typical conditions of a rocket engine. So 115 bars and 1500 kelvins. And then you add your solver. Okay, so it's just an algebraic solver. And you add two subdrivers to the solver. So you see that this time the add child syntax applies to a solver and not to a system. And those two run single case drivers will represent ground and vacuum conditions. So the next thing you do is you specify what conditions actually define your point. So here the only parameter that specifies it is the ambient pressure, 1 bar for the ground and 0 for the vacuum. And your system, your design system is simply declared. You want to add as a known the two geometric parameters, so throat area and area ratio between the throat and the exhaust and the outlet. And now the interesting bit is this: you see that we have equations, we have constraints on the thrust that we want to achieve, but in two different operating conditions. So a certain thrust on the ground and a certain thrust in space. And then you just run drivers, and CoSApp will solve for the two geometrical parameters in one go, satisfying the two conditions that are expressed in two different operating conditions. And that's something we do a lot in multidisciplinary design. Now, a word, I don't know how am I on time. Anyway, a word on dynamic systems. So you can have systems with time derivatives, so systems whose variables are known implicitly through their time derivatives. And so you need a time integrator to follow the trajectory of your system. But this time we can handle multi-mode system with discrete events, which essentially allow you to introduce discontinuities in your system. So it can be mode switching. The valve is shut or the valve is open, for example, which will be two very different modes of operations. You can also have contacts or impacts, failure modes, etc. So any kind of discontinuity you can model in your system with an event, and I'll show you an example in a minute. I should mention that it was an interesting collaboration with INRIA, who gave numerous talks during this conference. That's the French National Research Institute for Computer Science, very talented people. So events could be of two sorts. You could have primary events. So you see here we have a breakable system with very few variables, x and x max. And we say we have an event failure, and the event failure is characterized by the condition x is larger than x max. So in fact, this Boolean condition here is not considered as a Boolean variables, but rather it's interpreted as a zero crossing function, and it's interpreted as the moment when x becomes larger than x max. So you don't know if or when this condition will ever occur, but you can say, here's what's going to occur if this ever triggers. And so that's typically what you write in the transition method that I mentioned earlier. So here you say, if the event failure is detected, then you have this particular variable that we call a mode variable, because that's a variable that's allowed to change only during the event of during the triggering event. And you can say, in this case, the failure trigger will be none. So you see, not only can you make an event directional, you can say it's only when x becomes larger than y and not the other way around, but you can also make an event irreversible, because you can make sure that once the event has occurred once, it'll never trigger again. Okay, so that's typically what you want to do when you have failure mode. Secondary events, so the other kind of events, are typically events that are triggered by other events. So they're of different kinds. They can be completely synchronized events. So for example, you have a tank filling up, and you say when the level of water in the tank exceeds a certain critical value, then that triggers an alarm somewhere else, okay, and triggers a series of events. So you can do that. You can have filter events, so events that are filtered with a Boolean condition. I want such condition to occur and x be larger than 1, for example, okay? Or you can have merged events, which is an OR condition, and it's typically what I put in this somewhat lengthy example here, where you have a two-stage rocket, stage 1 and stage 2. So each of these stages in this example bear their own dynamic module. So they follow in time the acceleration vector and position in space. And here you have constraint. You have an inner constraint, so unknowns and equations, which typically say the external force acting on the two stages ought to be regarded as unknowns, so computed by a solver, so as to ensure that the acceleration vectors of the two stages are equal and the sum of the forces are 0. So essentially that means the internal cohesion forces of your system such that the rocket moves as one single object, okay? And then you say, we have an event, so a primary event, enter the stratosphere based on altitude, okay, easy enough. But the interesting bit here is this secondary event here, which is called detach. And notice that in the definition of the model here, you can leave the trigger condition blank. So that means that it's undefined, that will never occur unless you define it. Okay, so you can define the triggering condition in another context, not just the definition of the system. And so typically here in the transition, what we say is that if the detach event is present, then we clear the internal problem. So we relax this internal forces, cohesion forces conditions. We set the external forces to 0, and again we reset the trigger to none. So the detach event only occurs once. Okay, and so once you've instantiated your model. Here you have your rocket, and you can say, for that particular rocket, I want the detach event to be triggered by the merging of either the rocket enters the stratosphere or the bottom part runs out of fuel. Okay, so very simply and declaratively, you can define a quite complex dynamic object. So what happens in the time trajectory here, I represent any variable x of the system, which by no loss of generality represents the state of the system. And what we do is that we have a knowledge of the initial conditions, and we integrate by time marching with respect to the derivatives of this variable, and we compute in a continuous fashion what the trajectory of the objective. So that's very classical. And at the same time, we follow up in time at every time step. We evaluate this zero crossing function corresponding to each primary event. And if eventually one of these zero crossing switches signs, we know that everything is continuous at this stage. So we know that at some point that function has reached a zero value. We roll back in time. Okay, almost done. That's the last slide, I believe. We roll back in time, define the event time, and then we start a transition loop where we recursively call all the transition methods of all the system tree. And in there, it's an iterative process because you can have restructurations, you can have new systems, you can have new equations or Fourier equations that you've just seen. You can also have events that trigger other events and so on. So it's a game of dominoes falling. And we know that this loop eventually converges because once triggered, an event cannot untrigger. So when all the dominoes have fallen down, you just take a look and you have the final state, the final transition state of the system, and you can start off a new continuous time phase. And so we have a special algorithm that follows the system in both continuous and discrete time phases. And I'll finish by a quick summary. So I hope I will have convinced you that CoSApp is a very versatile and flexible tool to simulate and design system, from simple standalone model to more complex composite multidisciplinary assemblies, and that's typically the way we use it at Safran. It allows users to create modular simulation workflows with a clear separation between models and algorithms, so simulation use cases. And it handles both steady state and multimode dynamic systems. And with this, I'll thank you very warmly for your attention, and we'll be happy to answer your questions. You have the code is the link to the presentation. Thank you.
Thank you, Étienne. Any question? All right, I'm going to go to Mary first. Thank you for your presentation. I'm not working in physics any way or another, so it might be a naive question, but I had the feeling that Python was not a good language to solve that kind of physics problem because it was quite slow, actually, compared to others. So I'm quite surprised, and I would like to have your opinion on it.
So speed is definitely an issue, you're right. What you can play with is the magic combination of native code exposed with a Python interface, which you then wrap into a CoSApp system. So that works pretty well, and that's typically how we use it internally because you need the systems to be sufficiently fast for them to work. So yes, speed is an issue, but you gain great flexibility also. Okay, and so we put more emphasis on flexibility than sheer performance at that point. Okay.
Thank you for the presentation. I've used a similar setup in simulating computer graphics like fractures and those kinds of complex systems, where I built something similar from the ground up, solvers, like constraints. So I guess my question to you is, with regards to what's out there today that's quite similar, what were some of the deficiencies that you tried to address in CoSApp that perhaps weren't available in other sorts of libraries that also perform simulations and allow you to
So there exist several MDO libraries. Some of them are very good. Some of them are more suitable to large systems. Okay, here we're restricted to a few hundreds of variables essentially. But again, I guess the answer is along the line of what I've just said. We trigger flexibility of use and ease of use also. Some of them are quite. Some of those framework are hard to master, and you have to conform to a very strict mathematical logic before you can even start to use them. So we want to tackle the problem through another edge, and to bring the user a very simple interface, and as much as code can be. But that was the primary objective, to bring this to our engineers so that they can try things out.
Thank you so much, Étienne. So since the lightning talk is starting, we don't have time for more questions, but please reach out to Étienne if you still have a question. Thank you.